All right, let's get started. I'll begin with a word of prayer. Dear Heavenly Father, we thank you again for this afternoon. I thank you for these students. Just pray to be with us today. Help us to just glorify you, Lord, in what we do. I pray that you would help us to understand your creation more deeply through our study, Lord. In your name I pray. Amen. Okay, so today I'm going to talk to you about some of the deeper theorems of vector calculus, some of the second and third theorems of Green, and if everything goes well, hopefully I will explain to you mathematically why it is we can construct potentials, electric and the vector potentials for electric and magnetic fields. At the start of all this, though, I have a little bit of unfinished business about just electrostatics, three-dimensional electrostatics. We've gone through the same song and dance in 2 dimensions, but I would be remiss if I didn't talk to you about three-dimensional electrostatics. So the idea here is just that we have some charges, say Q1, Q2, Q3, and so forth. Let's say we have K of them. Well, how many of them? I don't know. I'll say K of them. I may regret that. Let me just check on that for a second. Now, we know from experiment that the electric field, which comes from these point charges, is the Coulomb field if we're very close to the charge. In particular, so the electric field, something like 1 over 4 pi epsilon naught. The electric field from the jth one, jth charge, and then I would divide by the length from R to R sub j, say squared, and then R minus R sub j, the unit vector of that. This is the formula for the electric field is the Coulomb field. I wrote it in the less, okay, so if it's at the origin, you can write this a little bit simpler. The electric field is just Qj over 4 pi epsilon naught, say, r hat over r squared, or in our usual notation in here, rho squared over rho hat, although I'm a little bit unwilling to write that because we use rho for charge density in electrostatics. Okay, so, if at origin, the formula above simplifies a little bit. Otherwise, geometrically, all that's saying is, and here I'm talking about the electric field at the position vector, at the field point R, that's coming from the jth charge Q. Now, I can imagine surrounding one of these little charges with like a little sphere, right? And what would if I call this sphere S1, say, what would the flux through S1 be? Mm-hmm. Yeah, the flux through S1 would be equal to so. Right, I guess technically speaking, it should be, E1 plus E2 plus plus EK, right? Dotted with ds. That would be the flux through a little sphere, which encloses the first charge. Now, what happens with the electric, so the electric field that comes from the second charge and the third charge and all the way out to the kth charge right? Those have zero divergence everywhere. I mean, more to the point, I mean, we just argued plain geometrically, if you like. The electric field from Q2, it's just going out from Q2 radially, right? And Q3, it's radially spreading out. This is the Coulomb field. What happens with the field lines that come from all the other charges through the sphere? Yeah, they just go in one side and go out the other. So every field line that comes in comes out. All the field lines that are cutting through S1 are completely from Q1. All right? That's the way it works. So basically, this is just equal to, E1.ds. Oh, sorry. And that is actually going to work out to, I think it's Q1 over epsilon naught if we look at the calculation. Tell you what, let me get the projector out. Let me get that projector out. If I can find my notes. I've given up on my previous computer. What? Voting? What are you talking about? Zach is predicting controversy in my comment section. I may have to turn the comments off. He might be right. I'm sorry, is this no longer a safe space for you? Have I hurt your feelings? Good gracious. I tell you, it is a sad day for America. Oh no. No, that's the right chord. I think you're right. I think it's worse than that. It's much worse than that. Oh. Oh well, it had a good life. As you can see, I've had official training by the IT department here. I can do everything they do. I'm sorry, did I say that? Oh, I'm just kidding. They're good folks. All right, let's see here. But they obviously have not idiot-proofed this, because here I am. All right, where are we? Go back in there, stupid thing. Well, how'd that get in there? Yeah. I mean, this is off up here, and I think I must have pulled the plug out. I think what happened is by pulling the cord, I somehow pulled the unit inside and unplugged it inside the box, which is locked, which I can't get to. But that doesn't bother me too much. What bothers me is that this I cannot get back up. Hey, we're fine. Okay, so what I was trying to get at over here is just this. You can calculate if you just surround one of the charges, if you surround one of the charges with a little Gaussian sphere, little sphere which just encloses the charge and none of the other charges, you can show that the flux through that sphere is just given by the charge that's inside the sphere divided by epsilon naught. The details of this calculation are actually in the notes. Okay, I was going to project them and show them to you. Sorry, can't do it. And you could do the same thing, right? You could also just as well surround, the jth one, say Qj, with a sphere Sj, which just contains this one. Almost the same calculation, almost the same calculation goes through replacing 1 with j, and so what I'm trying to say is this calculation, you can do it for each one of the spheres, right? So the flux that comes from the electric field, and I'm also supposing that there's this principle of superposition, that the net electric field is a sum of the electric fields generated from each one of the charges. This is the principle of superposition, okay? And so what I'm telling you is that we can calculate the flux around a little sphere that contains just one charge is the charge divided by epsilon naught, okay? And then what I can do is I can imagine taking a bigger surface like this one. It's hard for me to draw three-dimensional surfaces, so I'll just draw a two-dimensional. A big surface which encloses all the charges, right? And I can calculate what's the flux through the big surface of the total electric field, right? Well, it's going to be equal to the sum of the integrals over these guys, well, yeah, I mean, it's simple. Basically, this, I could write that. Right, which is, of course, in other words, it's Q enclosed divided by epsilon naught. Now, how do I know that the integral on the outer surface is just the sum of the integrals on the inner surfaces? What am I using? What I'm using is that the divergence of the electric field is equal to 0 for r not equal to one of the source points. And that's also, I also have that calculation explicitly in the notes that I can't project. So the divergence of, and this is the whole electric field, right? The divergence of the whole electric field is 0 everywhere between the point charges, so I can use the deformation theorem and I'm using, what's the term that I haven't written here? Remember we did Gauss's theorem, the divergence theorem with holes last time? So the holes are the S1, there's an S2 over here, and so forth, right? So if I take the boundary of S, it's the outer boundary, I'm using S as the outer boundary. You can think about the solid, which is what? So let's say S is the boundary of E is S. So the volume I'm applying the Green's divergence theorem to is E minus the first ball minus the second ball, and so forth. Just removing the K balls which are surrounding the charges. So on this kind of like piece of Swiss cheese, if you will, I'm applying the divergence theorem and using the deformation theorem to argue that the flux that comes from each one of the charges, they sum together to give you the net flux that goes through the outside. And this is Gauss's law for not just one charge, but many charges. To do the calculation directly is kind of a bear. So this section gives you kind of a way to do it bit by bit. Sorry, I can't project it. Oh. Of all the lousy days for the projector not to work. Goodness gracious. Now again, well, no, I go on. All right, so Green's identities and the Helmholtz theorem. Section 7.9 in my notes. Okay, so here's Green's first and second identities. We assume that f and g are twice differentiable functions on some domain d prime, where e prime is an open set. It's an open set containing the simple solid E, which has boundary piecewise smooth This does leave me with a certain question. What is d prime? I think d prime is supposed to be e prime. That's e prime. The typo in my notes. Let us not be distracted by that. So here's a picture. Here's your simple solid, E. And then E prime is just some fuzzy thing that surrounds it. That's all. Okay? That's all. Okay, so that's the preconditions. Here's the Green's first and second identities. First of all, the triple integral over the solid of the divergence of f dotted with the divergence of g, not divergence, gradient, dot gradient, integrated over the volume, plus the triple integral over the solid of f times the Laplacian del squared g dv is equal to the integral over the boundary of the of f times the gradient of g dot ds to the integral over e of f gradient squared g minus g. When I say gradient squared, I mean Laplacian. Do you guys remember what the Laplacian is? What is del squared? What does that mean? Yeah, I mean, in coordinates, it just works out to like partial x squared plus partial y squared plus partial z squared. It's just that second order differential operator acts on the function to give you another function, which is formed from second derivatives of the original function, which is why we're assuming that f and g are twice differentiable in order that these expressions are meaningful. So over here, I've got f gradient of g minus g gradient of f dot ds. This is most annoying. Okay, guys. So how would we prove these? I said they're homework in the notes, but I don't think I made them homework for you guys. Did I ask you to show these? I don't think I did. How would you work these out? Well, it's a relation between like a triple integral and a double integral, right? So these must be coming from the divergence theorem, right? So let's see, what divergence theorem could we look at? What if it's just that? I mean, so what did the divergence theorem say? Do you guys remember? The triple integral of the divergence of a vector field, let's say f, is equal to the surface integral of f. If this is so what does this suggest to me? This suggests to me that f is being played by the role. This would be my first attempt in the homework problem. I would just say, I'm going to try that and see if that leads me to what I want. So what's the divergence of this? Oh, wait a minute. We've got the divergence of a function times a vector field. We worked out the product rule for such things the other day, did we not? What was the product rule for this? It is the gradient of f dot the vector field, which in this case is the gradient of g, plus f times the gradient, the divergence of the vector field gradient of g. All right? Oh, fine. This is exactly this is what is meant by del squared g, the Laplacian of g. Done. Right? See it? Do we agree? It's just the product rule for the divergence paired with the divergence theorem. That's Green's first identity. It looks worse than it is. It's actually not hard. How about this one? Ow. Don't do that. It hurts. Looks like this time we're going to use the divergence theorem with something like, let's say, g equal to f gradient of g minus g gradient of f, right? And when you calculate the divergence of g, what do you get? Two product rules, right? The one product rule, you get nabla f dot gradient of g plus f Laplacian of g minus nabla g, or gradient of g, dot gradient of f, minus g Laplacian squared of f. The dot product being symmetric, these guys cancel. Commutative cancels, right? And what are you left with? This guy and this guy. And again, the divergence theorem completes the idea. At this point, you should be annoyed with me that I didn't give you this as homework, because this was an easy homework problem, right? Yes, okay. Don't worry, there's still the final. Okay. What? It's too soon? It's too soon, okay. All right, so definition. A function f is harmonic on E if the Laplacian squared of f is equal to 0 on E. Harmonic functions are very special. You could spend your whole life studying harmonic functions. Some people do. They even get paid for it. It can happen. Proposition 7.9.2 gives us a few properties here. So we're going to again look at a simple solid E, piecewise smooth boundary partially. Suppose F is harmonic on E. Again, E is a simple solid, all right? We have these things. One, the integral over the boundary of E of the gradient of F dot ds is equal to 0. 2, the integral over the solid E of the gradient of F dot the gradient of F dv, of course, is equal to the surface integral over the boundary of E of F gradient of F dot ds. Three, if f of xyz is equal to 0 for all xyz on the boundary, then that implies that f is identically 0 in the whole solid. That's weird, by the way. So you're telling me that this function of 3 variables is completely pinned down by what happens on this 2-dimensional skin of the simple solid. Like whatever happens on the edge of the simple solid for a harmonic function, it pins down what happens inside. Well, at least in the case that it's a constant on the outside. That's interesting. This has significance to, electricity, particularly the study of voltage and conductors. If the Laplacian squared of V1 is equal to B, and if the Laplacian squared of V2 is equal to B throughout E, and V1 is equal to V2 on the boundary of E, then V1 is equal to V2 throughout E. I do regret using E as the solid here because I'd really like to make a comment at this point about electric fields and potentials and such. But I guess I'm still okay. So yeah, let me make a side comment here before I forget. One of the reasons we're looking at this, guys, is Gauss's law for the electric field is that the divergence, there's a vector on the E here, so there's a little danger in confusing this E with the solid E, okay? So the divergence of the electric field is equal to rho over epsilon naught, where epsilon naught is the permittivity of free space and rho is the charge per unit volume. Rho is dq dv, okay? Talked about it the other day a little bit. Now, the electric field, on the other hand, can be derived from a potential. The electric field, at least in the electrostatic case, is simply minus the gradient of some potential function, let's say V. That's the voltage function, the potential energy per unit charge, just as the electric field is the force per unit charge. And so, when you combine these two things, what do you get? You get Laplacian, you get the divergence of the gradient of V is equal to, I'll bring the minus to the other side, minus rho over epsilon naught. Or if you like, the Laplacian of the voltage function is minus rho over epsilon naught. This equation is known as Poisson's equation. When the charge density, when the rho is 0, it simplifies to what's known as Laplace's equation. But Poisson's equation is really what you want to solve in order to find the voltage as a response to a certain charge distribution. What this says is that if you have two voltage functions, right? Think of B being b is a given function. It's the charge density divided by epsilon naught with a minus, all right? So what this number 4 says is that if you have two voltage functions which satisfy Poisson's equation, and if they match up on the boundary of the simple solid where you solve Poisson's equation, guess what? They're uniquely fixed to be the same throughout the whole thing. So what this says is if you're trying to find the voltage function, which is a solution to Poisson's equation, all you got to do is to match up the boundary condition on the edge, and that will uniquely fix the voltage function. That's the consequence of 4. That's why 4 is important. Now, so these you can also show through somewhat simple arguments. I mean, we could work these out. I think I'm not going to. These actually would still make decent homework problems or test questions, I guess. I don't know. Do you want me to pick one and do it? I think they kind of build on one another. Let's see here. How will we prove 1? I need to break from the hard stuff. Let's do this easy thing. So prove 1. What'd I do? I would use the divergence theorem. But hey, that's given to be 0. One down. How do you prove 2? Remember, I said f is harmonic. That means that we get this, which is that. Hey, I was robbed that time. Uh-oh, I don't think it's going to go better the second time. No, too high. All right. This one, what does this look like? What's at play here? It's the divergence theorem again. What if I put f equals to g in Green's first identity? What happens if I do that? Oh, maybe I should do. Yeah, I think if I put f equals to g, if I put f equals to g in Green's second identity, it is true but useless. First identity, if anything. So the gradient of f, that volume integral would be equal to. Now this is 0 because f is harmonic. We're assuming that. So the Laplacian is 0. And that is what we want. So this is immediate by putting f equal to g in Green's first identity. And then these guys, though, how do you prove these sorts of things? F equals to 0 on the boundary implies f is equal to 0 throughout the bulk. Well, if f is equal to 0 on the boundary, so here's how that argument goes. You take your region, right? E whatever. And so, maybe this is the boundary of E. Okay, fine. And we have that, the gradient. So, of course, the f is equal to 0. F restricted to the boundary of E is identically equal to 0. So what does that say? That says that this surface integral is 0. F is 0, right? Integrate 0, get 0. True for the integral you learned in Calculus 1. It's true for the integrals you did in Calculus 2. It's still true for these integrals. Integral 0, 0, 0. So this is 0. So we have that the integral, triple integral, of the gradient of f. What's the gradient of f dot the gradient of f? That's nothing more than the length of the gradient of f squared dv, right? F is assumed to be continuous. We're differentiating it, right? So it's certainly continuous. Can continuous functions just jump to be non-zero from being 0? just 1 point or something? No. The way continuous functions change is continuously. So if a continuous function is non-zero at 1 point, it's non-zero in a whole open set near that point. Which means I don't have the option. If I had that this function was non-zero in some little open set, that would mean that the gradient had to be non-zero, had to change from 0 to something. That would imply that this was non-zero. But we're adding together, we're integrating things which are positive squared. So if you think about it for just a little bit, and not a totally rigorous argument I was just giving you there, it's probably a way of making that rigorous with mean value theorem or something. Anyway, this basically implies that the length of the gradient of f is equal to 0, which implies that the gradient of f is equal to 0. But since E is a simple solid, this means that the gradient of f is equal to 0 on a connected set. And we proved before that if the gradient is 0 on a connected set, in fact, that implies that the function is constant. But that constant must be 0 because we already know that it's 0 on the boundary. And the boundary of E is contained within E. So there you go. The function has to be identically 0. Something like this is the argument. And 4 I'll leave to you guys. It's just the usual kind of thing. But Green's third identity, let me go on to that. I don't know if I'm going to make it through this lecture. I really needed that projector today. This stuff is considerably harder than other things we've done. Okay, so this is Green's third identity, which is not as easy. Green's third identity and so we have a simple solid again. Boundary of E is piecewise continuous, and we assume f twice differentiable throughout E. A little bit more though. Let R equal to xyz be a fixed but arbitrary point in E. And we use variables of integration r prime, x prime, y prime, z prime. So dv prime, for example, is dx prime, dy prime, dz prime. So we're using the prime variables to set up the integration. We're using x, y, z as a fixed but arbitrary point. This is opposite our usual practice. Our usual practice is to use x and y and z as integration variables. Okay, but here I want x, y, z to be an arbitrary point, so I can't do that. I should mention to you, of course, this is all loosely speaking based on a proof I found in Susan Culley's vector calculus book. I should give credit there. That's where I personally found this. If there's any errors here, they're mine, probably not hers. But this is based on that. Oh, anyway, so getting back to work here. And the gradient, like we are also differentiating with respect to the prime variables. So nabla prime would have the meaning x hat prime, partial x prime, plus y hat prime, partial y prime, plus z hat prime, partial z prime. All right. With this notation in mind, we have the following. F of r is equal to minus 1 over 4 pi, triple integral, over the solid E of the prime Laplacian squared of f of r prime divided by the length of r minus r prime dv prime plus, I'm going to write it under actually, plus 1 over 4 pi. Well, no. I don't know. I'm going to regret whatever I do. 1 over 4 pi surface integral over the boundary of E minus f of r prime gradient nabla prime of 1 over the distance between r and r minus r prime, close big bracket, plus the nabla prime of f of r prime divided by the length of r minus r prime, close big parentheses, dot ds vector. All right. This is Green's third identity. If I give this as a homework problem to Calculus 3, it means I have some sort of vendetta with them or something, I don't know. I would only give this as a homework problem to my enemies, or maybe a student I really wanted to learn, enjoyed hard problems, I don't know. This is not like those. This is going to require some effort to prove, all right? But before I do that, just stop and appreciate what this identity is. Look at it. What is it? It's saying the value of the function, right? The value of the function at a point inside the solid region E is given by this particular volume integral and that particular surface integral. What is the volume integral? The volume integral is integrating the Laplacian squared, right? And then over here, you're taking the surface integral. It's although it does seem to be, well, there's an f over here too. I guess it's not an entirely explicit formula. There's still an f, but anyway, it's just a very, very intriguing formula, this formula. All right, so here's the first, to prove this formula, there's a series of steps that we have to go through. The first is this lemma. Lemma 7.9.4, and it states that the limit as r goes to 0 from the right of the integral over s sub r, and that's a sphere, spherical shell of radius r, guys, h of r prime over the length of r minus r prime ds, well, that's equal to 0, given, what are we given? We're given that h is continuous, okay? If we can understand the proof of this lemma, we don't need to go through the proof of the harder lemma. It's essentially the same argument. So I'll try to go through this one a little bit slowly. I'm just going to gloss over the other one. So what is SR? SR is basically the set of points. It's R prime such that what? Right, that's the condition. Distance R from the center point R. So just to emphasize, this SR, it's like this. The center point in it is the fixed point R, and so a point out here is like R prime. So this is the SR I'm talking about. All right. Okay, so there's a typo in the notes right here. Not terribly critical, but it's easy enough to spot. So the integral over the SR of h of r prime over the length of r minus r prime ds is just equal to what? So I have that repeated in the notes twice. What I meant to write in the second step was that because you're on the sphere, the denominator is just r. So we can pull it out, it's a constant. And so what we're left with is 1 over r integral over the sphere of h of r prime ds. Now this is a surface area integral, all right? Now here's the step which is something that you guys might not think of because we don't do these kind of arguments too much in calculus at this point. We did more of them in Calculus 1 if you took it here, but for some reason, well, it's partly my fault. I could have done more of this kind of stuff at various points in the course, and I just shy away from it because I know you guys don't like it. Well, I don't know. You make up my excuse for me. Anyway, so the point here is that if H is continuous, it follows that there exist vectors A and B. There's some points A and B in here such that H of A is less than or equal to H of R prime is less than or equal to H of B, right, for all R prime in SR. How do I know I can do that? How do I know I can find a minimum and a maximum value which is attained by this continuous function? Well, it's a sphere. That's a compact set. The extreme value theorem of topology applies here, and there's a deep analytical result which says that you can find such, it has to attain its min and maximum because it's continuous and because we're talking about a compact set. In other words, it's extreme value theorem, basically. Now, consequently, you can, of course, divide this by what? These are always R minus R prime. If you can't make out my writing, it's always the same thing, okay? I really should have just called that thing Pac-Man and just wrote Pac-Man a bunch of times or something. Now, I could write R, yeah. But the reason I didn't do that is simply this, is that this implies then that, but yeah, these are, I mean, fine. I will succumb to this pressure. So if you take the surface integral of this inequality, you can do that. If you have f is less than g, the surface integral of f is less than the surface integral of g. There's also a kind of like inequality preserving properties of scalar surface integral. So what that gives me, of course, is the surface integral of h of a ds over r less than or equal to 1 over r integral of h of r prime ds. See what happened? Curses. Less than or equal to integral of h of b ds over r. Okay, but these are just constants, right? What's the surface area of a sphere? Right, so I get 4 pi r squared divided by r, which gives me 4 pi h of a r, less than or equal to integral of, 1 over, well, the integral h of r prime, the thing I'm trying to show goes to 0, right? And that's less than or equal to 4 pi r h of b. Am I out? We good? Oops, sorry. And then what happens as r goes to 0, what do you get? The thing below the integral goes to 0. The thing above the integral goes to 0, because h of a and h of b are just constants that are, they're bounded. They can't they can't blow up, right? In fact, a and b also both tend to r for what it's worth. What you're looking at is r times h of r as r goes to 0. And so by the squeeze theorem, we get that the integral Es bueno. Well, anyway, we did it. All right, the next one. Projector. It's hopeless. The next lemma, if you'll, I need to erase these. The proof is essentially the same spirit as the one we just did, but the details are more involved. It's on page 405 of my notes. So on page 405 of my notes, the next lemma happens. The next lemma is this. The limit, as r goes to 0 from the right, of the integral over the sphere of radius r of h of r prime, gradient prime, 1 over length of r minus r prime dot ds vector is equal to minus 4 pi h of r. Again, like I said, the proof is very similar in spirit to the one I just did. It involves a squeeze theorem argument, and you actually have to get into the differentiation with respect to the prime coordinates. But it is relatively straightforward. I would love to project it and show it to you, but I just can't. All right, so now let's try to put it together. So what I want to do then is I want to use Green's second identity on a solid region with holes. And what solid region am I going to look at? I'm going to look at E prime, which is actually going to not be the E prime I talked about over there. Or is it? Well, I don't think that's coincidental. It's not the same E prime. This E prime is, actually E prime is E. Sorry. E minus the ball of radius r, all right? Where BR is the closed ball of radius r, which takes as its boundary SR. So here we have the boundary of BR is equal to SR. And SR, this is the point which contains, it contains the fixed but arbitrary point r, right? The XYZ point we started with. And so here's a picture. So like here's the, well, let me be more careful. Here's the point R. So this is, here's the little ball of radius r there. And here's, E. Here's the boundary of E, right? And so we can apply Green's second identity to this region with a hole. I can do that, right? Because we have the divergence theorem for simple solids with holes, right? Green's second identity, which is built from the divergence theorem and a simple argument. So I just use Green's second identity on E prime, which is a simple solid with this spherical hole in the middle. And what that gives me, and let's see, and so with a little bit more fine print here, we're using G of r prime is equal to 1 over the magnitude of r minus r prime. Okay, so what is f? Well, f is f. Okay, so we have then is the integral over E prime of f of r prime Laplacian prime squared 1 over magnitude of r minus r prime minus Laplacian prime squared of f of r prime divided by the length of r minus r prime dv prime is equal to integral over the boundary of E prime of f of r prime nabla prime 1 over r minus r prime minus nabla prime f of r prime divided by length of r minus r prime dot ds. All right. So you see what I did, though. I just used Green's second identity with g equal to the reciprocal of the distance function here. What is it? So basically then I simplify this term. Where was it? I find a way to rewrite this term so first of all, I show through explicit calculation that this piece is 0, which isn't terribly surprising, because when r is equal to 0, we've already done that calculation in the ordinary case, like the divergence of the reciprocal distance function is 0. So certainly well, anyway, I think we've done that before. Anyway, the calculation is on page 406 of that. Then I look at the triple integral over E prime of I look at just this, well, this right here. That's exactly that. And I show that this can be rewritten as what? Oh, I don't do that. I say, so then this is equal to that, right? F that minus gradient of that. And then what do? Oh, and then this breaks up into two pieces, right? On the one hand, you have the boundary of E, and on the other hand, you have what? Minus SR, right? Why minus SR? It's in here, right? So this has normals pointing out, right? But the normal has to point in order to use Green's divergence theorem with a hole. So then this breaks up into two integrals. One is the integral over the boundary V. The other is the integral over the little sphere of radius r. But for the little sphere of radius r, as we take the limit as r goes to 0, what do we get? On the one hand, we get this. This term just sits there, right? 1 over 4 pi integral over the boundary E of this stuff. That's exactly. Look at this. This is pretty much exactly this, right? With E prime replaced with E. So and then of course this is pretty much this, right? So the question is, where's the 4 pi coming from, and where's the f of r coming from? It's all coming from the integral of the inside. When I erase this, right, and look at SR, what happens? You've got, on the one hand, the gradient prime of fr prime over this, right? I've got this term right here, right? This is like that. It's a continuous function divided by length of r minus r prime. And then this one is what? This is like h. It's like the h. And the gradient prime of that